Let's look at an example of melting ice to boiling and see how much energy that takes. So I'm just going to make a graph here we're going to look at the temperature as a function of time. So as we begin to heat this water up, what's going to happen? And let's start with it at a relatively cold, let's say -5°C, and we go to 0 here, and let's say we have 10, 20, all the way up to boiling here, 100 degrees. So it's not exactly to scale there. And then we have time here, depending on how fast we dump the energy in. So the first thing you'll notice is when we break this up, we have to heat this ice up to 0 degrees before we can start melting it. So this represents change in temperature as a function of time, and that amount of energy that's necessary to do that is going to be given by our mc delta T. So delta T is 5 degrees because it's a change in 5 degrees, C is the heat capacity of ice, and M is the mass of ice. Then we go to melt this. Now while it's melting, the temperature is not changing. So the energy needed to melt it is going to be the mass times the latent heat of fusion from ice to water. Once that occurs, so we've got our heating of the ice phase. This is our melting phase for melting the ice. And then once we melt the ice, then this is going to continue to go up as the temperature rises to 100 degrees centigrade. So this is where we're heating the water. So we're heating the water here. Over here we were heating the ice. And then we can boil it. And at this point, the temperature is not going to change. That's where we're boiling. In other words, we're doing a phase change from liquid to gas. And each one of these is going to take a different amount of energy. We could say that our, let's call this 1, 2, 3, and 4. Energy of 1, since we are just heating, is going to be the mass of ice times the heat capacity of ice times the change in temperature. Q2 is going to be equal to the mass of ice times L. Q3 is going to be equal to the now mass of water, which, assuming we didn't lose any, is going to be the same as the mass of ice times the heat capacity of water times delta T. And then our last energy here is going to be the mass of water times the latent heat of evaporation. So this is the latent heat of melting or freezing, and this is the latent heat of vaporization. So what do I know to solve these things? I know that the temperature change here is 5 degrees, and the temperature change here is 100 degrees. If I look up the specific heat of ice, it is 2040 joules per kilogram. The latent heat of fusion is 3.4 times 10 to the 5 joules per Kelvin, or per kilogram. No, sorry, just joules. No, that's right, joules per kilogram. This is joules per kilogram Kelvin. And the specific heat of water is 4184 joules per kilogram per Kelvin. And the latent heat of vaporization is 2.3 times 10 to the 6 joules per kilogram. And now we just have to ask ourselves, well, how much water are we interested in? So let's take 1 liter, which is 1 kilogram. So let's just look at a mass of 1 kilogram. So if I want to go ahead and calculate those out, then my Q1 is going to be equal to 1 kilogram times 2040 joules per kilogram per Kelvin times 5 degrees Kelvin change. So my units are all going to work out, and that's going to give me, let's just say 2000 times 5 for round numbers. It's going to give me 10,000 joules. Okay. Q1 is the heat needed to melt it. So again, I'm going to have 1 kilogram. That's going to be multiplied by 3.4 times 10 to the 5 joules per kilogram. So that's just going to give me 340,000 joules, just to make it comparable to that. Q3 is, again, 1 kilogram. I'm going to multiply that by the specific heat of water, which is 4184, but this time I have to go 100 degrees from 0 to 100. So that's going to give me roughly 420,000 joules. And then finally, to boil it, take that 1 kilogram, multiply it by 2.3 times 10 to the 6 joules per kilogram. So that's going to give me 2,300,000 joules. So if we look at that, just comparing this, the vast majority of the energy goes into boiling the water, the second is heating it, and the third is melting it. Very little required to heat the ice up 5 degrees.